And since people are coming, so let's wait for 2 more minutes. Okay, thank you. We can start our tutorial now. Hello, everyone. Uh, my name is Wen Qifan from the Hong Kong Polytechnic University. Welcome to join our tutorial. Here, I will co-present this tutorial with Xiangyu Zhao, Yejing Wang. They are from the City University of Hong Kong, and Huifeng Guo, Bo Chen, and Yueming Kang, and they are all from NOAA's ARPANET. And today we will talk about the automatic machine learning for recommendations, fundamentals, and advanced. And you can get more details about our tutorial in this website, and as well as our recent research survey paper. So let's get started. Okay, so first, what are recommender systems? Recommender systems are information filtering systems and aims to address the information overload problem. They try to filter some items and suggest relevant items to users based on their unique needs and preferences. Here, this item can be any products, people, and news, movies, etc. Actually, the recommender systems are everywhere in our online world, especially at many user-based online servers, like the e-commerce and the social medias, etc. So when you open a website and you type the URL linked to the website, you can see recommender systems there. And no matter you use your cell phone or your PC or your laptop. So when you browse into search websites, you can see some recommended items. So let me give you some examples. So the first example is from e-commerce, such as the Amazon and eBay. Of course, we have the Taobao and JD.com in China. Here is an example on Amazon. This is the most frequent recommendation scenario. I believe a lot of you know it. So when you want to buy a product like a book, the system would recommend a package, book A, B, and C to be frequently purchased together. Another example is from the content sharing website, especially like the new and the video sharing websites like the YouTube or the TikTok. Again, when you enter into these web servers, you can get their information there. Sometimes on the first page, you can see these recommended videos or something news, right? Another example you are interested in, we are also can recommend people in our online world, right? Like in this kind of this social networking or these social medias, such as the Facebook and LinkedIn. In China, we have the Weibo. Typically, for these websites, you will get something like friends, or they will show to you and they will recommend you you some potential friends you want to connect. Okay, so here I want to go through an example to show what a typical setting in recommender system. So here, this example is from the movie recommendations. We have items, that is the movie, right? We have earned users. Users can rate their movies to indicate their preferences in each movie. For example, here we may want to use a 1 to 5 rating star system, where a 1 represents I hate it, probably 3 is neutral, and 5 as I love it, right? Of course, in other websites, probably we don't have this kind of awaiting informations, but we have other interactions between the users and items. For example, in YouTube, probably we can connect these videos, and we will comment on these videos and so on. And beyond this kind of interactions between the users and items, we can have some side information about the users and items. For example, for the movie, we can have some side information like the product years, or who are the actor, and the review comment. And for the user, we also can have some additional information. For example, we can have their profile, and in some case, like in Facebook or LinkedIn, we can have this kind of social relations to indicate the relationships among users. For example, from this example, we can see for typical recommender systems, the input to this system typically is the historical user item interactions. And of course, if the site information is available, we can also put this site information into the system to help solve some specific problem. Maybe this problem cannot be solved by using the user item interaction only. And actually, this site information can further help enhance the recommendation performance. So what we want to do in recommender systems, we want to predict how likely a user will interact with a target item. Of course, in different scenarios, the interactions can be defined differently. For example, in e-commerce, probably we want to predict whether this user is interested in items, or whether this user will connect the item or weigh this item, even buy these items, right? So in different scenarios, we can have different definitions about interaction. But the overall goal for recommender systems is try to predict more potential interactions. Okay, so one popular technique to achieve the goal is our collaborative filtering. Basically, the basic assumption of collaborative filtering is similar users will have similar preferences. So that's why we usually use their historical data to get similar users. And then in the future, we can use this kind of similarity or similar users to make predictions. And one typical way to do is how can we improve their preferences and learn their representations. And then once we get their representations, we can calculate their similarity, or we can do some other scoring function, right? And so here, we still use this movie example to illustrate. Basically, this user item historical interactions, we can represent this as a user item rating matrix R. Here in this matrix, we have a lot of missing value. Actually, this matrix is quite sparse, and a lot of entities are unknown. So the task here, what we want to do is we can learn representations of items and users based on these observed entities in this matrix. So once we learn these representations, we can make a further prediction. Okay, so we can see, as we mentioned, for collaborative filtering or other recommendation techniques, the learning representations is the key for their success. So when we mention the representation learning, probably the first technique in your mind is deep learning, right? So indeed, we are now in the eras of deep learning because of their promising performance. So for example, here we showed is in some area, deep learning can achieve better performance than our human, especially in specific data set and in typical tasks, right? And of course, we can also have another popular examples or popular area like the in speech recognition or the natural language processing in such kind of area. So here, probably you have the questions. Can we extend the success of deep learning into recommender system? The answer is yes. So that's why recently we can see a lot of research paper proposed in academic. Also, there are some deep learning technique are applied into industry. So driven by this recent advance in deep learning, there has been increasing interest in developing deep learning-based recommender systems. In general, the architecture of deep recommender systems mainly consists of these following key components. So the first component here is the data input layer. Here, we aim to select a subset of relevant features for building recommendation models, including probably especially the user item interactions, right? If the site information available, then we can include the user profile and the items attributes. And in the embedding components, most recommendation models first transform the role user and item features into one hot vectors, and then embed them as dense representations via the feature embedding layer. Next step is the important step is the interaction components, which perform the nonlinear feature interactions so as to learn high order feature interactions, as well as to learn the nonlinear relations between the users and items. And for the whole model, we also need to consider other factors about the proposed frameworks and about the training procedures from the perspective of the system design. Here comes a question, and can this deep recommender architecture be generalized to all kinds of data or different recommendation problems? I believe the answer is no. In this kind of general architecture, and at each component, we may have different designs and operators. So to build a recommender systems with specific data or the particular problem, the most common practice is to design and trim different components in a handcrafted way. For example, we need to heavily trim the embedding side in the embedding components, right? And also, our human experiment or the expert domain knowledges are needed to select the suitable interaction operators from the inner products or the outer product or the convolutions, etc. So what I mean is, although deep recommender systems show their promising results, they still suffer from a manual design issue. For here, for example, first they heavily. Sorry, can we mute some guy? Okay, sorry.
So what are the results of our work so far? We started with.
Sorry, who can help us mute our audience? There's some noise. Okay, I can continue. So first, they heavily require expert domain knowledge in deep learning or the recommender systems. And second, the engineering effort and the time cost are required to decide the task-specific components for different recommendation problem. First, the human, our human bias or the error can easily result in suboptimal recommendation architecture. So to address the issue we mentioned before, in recent years, the automatic machine learning, AutoML, as one of the most promising AI technique, have shown its great capabilities to advance our deep architecture design from the manual to automatic. So that's why recently we also can see a lot of algorithm and architecture are proposed to apply the auto, auto, AutoML technique into the deep recommender systems. So that is also the focus of our today's tutorial. So by incorporating the AutoML into the deep recommender systems, and different models can be automatically designed according to different data or the different problem setting. And then to improve the predictions of the recommender systems, also enhance the generalization. Besides, it's also helpful to reduce the negative influence from our human bias or the errors, and significantly reduce artificial and time costs. Okay, here is a brief agenda for the following tutorial. In the following tutorial, we will first discuss about preliminary of the AutoML technique. This part it will be given by Xiangyu Zhao. Then Bochen will discuss about the embedding and interaction component. After that, the Yejing Wang will introduce a comprehensive search and the system. And thus our Xiangyu Zhao will conclude this tutorial along with some future directions. Okay, here is another thing is here is our very comprehensive survey paper. It will give you a very comprehensive understanding on this topic. So so that is a brief introduction about our tutorial. Also, the topic we will cover during this tutorial. Now I will end my part and will hand over this tutorial to Xiangyu. Xiangyu.
Okay, thank you, Wenqi. Thanks for the introduction. Let me share the screen. Okay, can you see my screen now?
Yes.
Okay. Hello, everyone. I'm Xiangyu Zhao from the School of Data Science at the City University of Hong Kong. In this part, we will introduce the preliminary of automatic machine learning and neural architecture search. So I think one of the reasons why you are listening to this tutorial is somehow you believe in the success of AI. So in recent years, there are many very successful AI applications in all the kind of fields, like chemistry, medicine, intelligence production, recommendations, and many, many more, even in arts, right? And so there are many AI applications, and more people will work in AI. So I think some of you already have experience in developing AI applications. So you may know that in these days, if we are talking about AI, it means somehow machine learning or even deep learning. And of course, that's only one. So if you would like to apply machine learning to a new task, you need to consider the following things. First of all, you need to define your task based on your domain knowledge. And secondly, you need your data. So you need to sit there and try to collect the data set from many sources. But what I'm most interested today is the third part, which is machine learning, and how do we process our data and the way that we get a prediction. So we can then define the machine learning pipeline. The machine learning pipeline usually consists of data cleaning, feature engineering, model training, and maybe even some kind of post-processing. So actually, all of these components, they have different kind of algorithms. And these algorithms maybe even have some hyperparameters you have to deal with. And then only the best combination of all of them can lead to the best performance, and you can deploy it in the commercial system. So actually, this is quite difficult, right? So you need some kind of experts being knowledgeable in all kinds of these parts, trying to figure out what's the best combination. But unfortunately, the task to figure out the best combination is very tedious and very time consuming. So people have to sit there for maybe for weeks, for months, and even longer to figure it out. So that's the reason why our goals, we aim to support developers and automating this part. Okay, so what we are trying to build is an automatic method, which simply prepares the machine learning pipelines given your data. And the overall mission of AutoML is to enable users to efficiently apply machine learning for the new AI task and the new data sets. Then if we use AutoML, we can automatically make these system design decisions. But in particular, if we go into the direction of deep learning, what we need to talk about is the architecture of the deep neural network, like how many layers, how many neurons, what kind of operations, and what kind of connections between the operations. So you now have a lot of design decision again, and this is really depends on your deep neural network, whether it's perform well or not. So actually, the problem of neural architecture search or NAS is to find the neural architecture A, such that the deep learning works, deep learning methods, they works best for the given data. And it is measured by the validation error of this architecture when you train the weights for that architecture. And I will call this weight as W star of A. Then this is the formal problem definition, and we are trying to minimize the validation loss of the architecture, which is with the optimized parameter W star. And here the optimized parameters means that we try to optimize the training loss with something like SGD for this particular architecture. So here we call the upper formula as the outer level problem or the architectural problem. And we call the lower formula as the inner level, which is to optimize the weight of the neural network. So you can think this is a bi-level optimization problem. And this paper, Neural Architecture Search with Reinforcement Learning, was published by Eclair, by Zoff and Lee. And since then, this problem, Neural Architecture Search, hit the mainstream, and we have seen exponential growth of the number of NAS papers published every year. Okay, next we will talk about the major components of NAS. Typically, NAS is a system with 3 major components. The first one is the search space. So search space defines a set of operations such as convolutions, pooling, or MLP, and how to connect these operations to form a valid network architecture. So the design of search space usually involves human expertise. So this process will also introduce some human bias. The second one is the search strategy. A search strategy will sample a set of network architecture candidates or we usually call them as the child model, and receive the child model performance metrics as reward, such as high accuracy or low latency. And it optimizes to generate a high performance child model. And the third one is the evaluation strategy. So here we need to estimate or predict the performance of a large number of proposed child models in order to obtain feedback for the search algorithms to learn. And conventionally, this was often done by training a network from scratch, but its process could be very expensive. So that's many new methods has been proposed to save time or computational resources, such as weight sharing or one-shot models. This we will introduce later. Okay, then I will introduce the techniques of the searching algorithms. And as I mentioned, the first paper that makes the NAS problem popular is this paper, Neural Architecture Search with Reinforcement Learning. And what was really great is that for the first time, this paper actually yield a state-of-art result for the real-world benchmark such as Cipher10 or PentryBank. And another thing that got a lot of attention is that they said that it also took a lot of computational resources. And they actually used 800 GPUs for 3 to 4 weeks. And in total, they trained 12K and 800 architectures. So this shows that if you have a very large computational power, you can find better neural architectures than human designers. So how did they use reinforcement learning for this? They have a controller, which is a recurrent neural network. And this has a probabilistic output. So you could sample the architecture from this with a certain probability. And then you can train this child network with the sampled architecture to get an accuracy as a reward. And then you can compute the gradient of these probabilities and scale it by this reward to update the controller. So let me talk more in details so about this reinforcement learning approach. So here is the hyperparameters of the CNN neural network, convolutional neural network, such as the filter height, filter width, and the number of filters. And these filters were represented as a string in the RNN controller. And all of the CNN layers have this type of hyperparameters. So if you have a new CNN layers, then you need to sample this type of hyperparameters again. And as I said, when we update the width of the controller by reinforcement learning, which is the approximate gradient scaled by the reward. So this is a reinforcement learning method. Okay, another NAS approach is actually just hyperparameter optimization, because in the end, all you care about is that you have the values of the number of filters, filter height, filter width, and so on. So you could directly work in this space. So in this CVPR paper, in fact, they came up with 2 cells, and each of them had 25 decisions. So you could just use a single space of 50 categorical hyperparameters and use this to directly optimized by the hyperparameter optimization techniques. So here is a one-to-one correspondence between the neural network search and the hyperparameter optimization. And another approach that was used for NAS is neural evolution. In fact, since 1990s, this was typically used for search for both the architecture and the width of the neural networks. And more recently, this ICML paper, they just use SGD for training the neural networks and only use the evolution in order to search over the network architectures. And here you can see a figure where you can see that in the beginning, you actually have a very simple architecture. And over time, you discover more complex architectures, and actually their performance is very well in the end. Okay. Okay, so the reinforcement learning and the evolution search methods are actually black box methods. And typically the black box methods need a lot of computations to find the best neural architectures. For example, on the CIFAR-10, reinforcement learning and the evolution need at least 2,000 GPU days to find the best neural architectures. So next, I will talk about the speed up techniques for NAS. And there will be 4 types of techniques here. And today I will introduce the first 2 due to the limited time. And the first one is the weight inheritance and the network morphism. Okay, so the network morphism are the operators that change the network architectures, but not the model functions. So that means that for every input, after you apply the network morphism, the network yields the same output as before. For example, you have this pre-trained network, and you put in a layer, and then your network become this one. And we say that this layer is just an identity mapping. So then the output from this modified architecture is still the same as before, right? Because this is an identity mapping. And you can use this network morphism in NAS as the operators to generate the new network. And you don't need to train from scratch because you have a pre-trained network available, and you can just fine-tune it, okay? So this allows us to begin with some models that have a certain performance, and we can do the fast architecture search. The second speed up method I want to talk about is weight sharing and a one-shot model. The most popular approach in this domain is DART algorithm. This DART stands for the Differentiable Architecture Search by Liu et al. At Eclair 2019. So its pipeline is shown in this figure. And you have this discrete architecture search problem where you have operations on the edge, and you want to choose between the different operations for each of these edges. And in particular, in this figure, you have the red operation, the green operation, and the blue one. For example, 3x3 kernels, 5x5 kernel, max pooling, and so on. And then the DART method relax this discrete NAS problem where you can only choose one thing. And now you can use all the different operations between these edges, and we put weights on them. So this is a mixed operator between node I and node J, and it's just a weighted sum of the individual operations, and the weights are these alphas. And here the alphas are called the architectural parameters. And then you can actually use gradient descent methods to optimize these alphas, because the alpha is a continuous value. And you solve this bi-level optimization problem, and you look for the alpha that give you the minimal validation loss. Okay, so this is a typical pipeline for the search stage, where you go from here to here, and some of the edges become stronger and some of them become weaker. And the last step in DART is to discretize each of the edges again. So in this figure, only the strongest edges remain and the weaker edges just go away. And then you can have a single architecture again, not this weighted sum manner. Okay, that's the DAT approach. And this model is very popular because you can actually solve this bi-level optimization problem by just doing a gradient step on the alphas and followed by a gradient step on the V's and a gradient step on the alphas and on the V's again and again. So this is a very, very simple algorithm, and there is no proof of convergency or anything. But it actually works very well in practice to find the best architecture. And also because its simplicity and the fast speed, most AutoML for recommendation models use this method. Okay, next our tutor Chenbo will introduce how to use AutoML to find the best embedding dimension and the feature interaction. And Yejing Wang will introduce how to conduct a comprehensive search of the recommended system by AutoML. Thank you.
Okay, thanks, Professor Zhao. Let me show the slides. Okay, can you see my slides?
Yes. Yes.
Okay.
It's okay.
Okay. Hello, everyone. I'm Bo Chen from Huawei Northside Lab. In this part, I will present some AutoML-based solution for the embedding component. Different from the computer vision, the input feature used in the recommender systems are very sparse and high dimensional. To solve this problem, neural network-based model leverage a feature embedding layer to map the high dimensional feature into a low dimensional latent space. For a feature field, we assign each feature with a dense embedding vector and then save all the vector in the embedding table. The embedding layer is an important component for the recommender systems as the number of parameters is concentrated in the embedding table. The feature embedding layer not only directly affects the storage capacity and the inference efficiency, but also has a very important effect on the prediction accuracy. To improve the prediction accuracy, save the storage space, and then reduce the model size, AutoML-based solutions are proposed for the learning of feature embedding. The intuition behind is that assigning higher dimensional embedding for the high frequency features can improve the model capacity. Besides, the low dimensional embedding for the low frequency features contributes to preventing the overfitting. According to whether or not the optimal embedding size is searched for each feature value, this solution can be divided into two categories: single embedding search and the group embedding search. The first one is the single embedding search, which aim to search the optimal embedding dimension for each feature value. Therefore, this method will face a huge search space due to the large vocabulary size. To select suitable embedding dimension for different feature values, AMTL adds a mask layer on top of the embedding layer. This mask layer can learn a mask vector to drop the undesired dimension of the embedding vector for each feature value. To avoid the unbalanced parameter update due to the different feature frequencies, AMTL proposes a tree-based architecture. The architecture has two branches, which are used for high frequency and low frequency feature. A weighted sum operation based on the feature frequency is used to merge the result of the two branches. To obtain a hard mask layer while making the learning process differentiable, a softmax function with a temperature hyperparameter is used to relax into the continuous space. Similarly, PEP proposed a pruning-based solution by enforcing column-wise sparsity on the embedding table with the L0 normalization. Therefore, some elements are set to 0 so that the embedding size can be reduced. For example, as shown in the figure, the first value in the embedding V1 is set to 0 and proof. Therefore, the embedding size of this feature can be reduced. And some unimportant feature embedding like V3 are dropped by setting all the values to 0. However, as L0 normalization is NP hard, PEP takes a soft threshold reparameterization to achieve the similar purpose. GS serves as a learnable pruning threshold with a softmax function. When the absolute value of the embedding parameters are lower than the threshold, PEP will prove this value and then set them to 0. It is obvious that the search space of AMTL and PEP are highly related with the embedding size D. To reduce the search space, a solution is to divide the embedding dimension into several column-wise subdimensions, just like auto-embedding and ESAPN. By doing this, the search space is no longer related to the embedding size, but to the number of predefined subdimensions. Auto-embedding and ESAPN reduce the search space by dividing the embedding dimension into several candidate subdimensions, shrinking the search space compared with the AMTL and PEP. They share a similar motivation to search different embedding size for different user and items. They claim that the low-frequency user or item may achieve better performance when assigned a smaller embedding size. On the contrary, high-frequency user or item may need larger embedding size, since it can provide more parameters and achieve better capacity. Therefore, searching embedding size for different user and items dynamically can receive better performance and is more efficient in memory. Auto-embedding leverages two controller network to decide the embedding size for each user and item, and then perform a soft selection strategy by summing over the candidate subdimensions with the learnable weights. Specifically, auto-embedding first defined several candidate embedding subdimensions, and then perform embedding lookup to obtain multiple embeddings. Then, to transform various embedding dimensions into the same dimension, a linear transform layer is used to unify. A linear transform layer is performed to transfer the various embedding dimension into the same dimension. Then, a batch normalization with the 10H function is used to unify the scales. The controller network uses the feature popularity and the context information, such as the hyperparameter and the loss, as the input for the MLP, and then output the selection weights. Finally, the weights produced by the controller networks are leveraged to aggregate these representations. The optimization is achieved by a bilevel procedure, where the controller parameters are optimized upon the validation dataset, while the model parameters are learned on the training dataset. Instead, ESAPN performs a hard selection strategy through the policy network or the reinforced learning. Similar as auto-embedding, firstly, each feature obtains multiple embeddings through candidate subdimensions, and then pass over the linear transformation layers, batch normalization layers with the 10H function to obtain the comparable scales. Then, two policy networks serve as RL agents for the user and items, which adjust the embedding size dynamically. The policy network takes the feature frequencies and the current embedding size as the input, and then leverage a MLP to predict the probability of choosing to action, namely enlarge the embedding size or unchanged the embedding size based on the reward returned from the recommender model. Finally, each user and item converts to an optimal predefined embedding dimensions. The second one is the group embedding search, which search the optimal embedding size for a group of feature values rather than a single embedding, rather than a single feature value. Auto-embedding and ESAPN shake the search space by dividing the embedding dimension into several candidate column-wise subdimensions. Another solution is to group the feature value of a field based on some indicator, such as the frequency, and then assign a row-wise group embedding dimension for all the values within the group. By doing this, the search space is no longer related to the number of feature values, but to the number of predefined feature groups. A specific case is setting the number of groups as 1 and then searching a global embedding dimension for all the feature values of the field, such as AutoDim. AutoDim is designed to select optimal embedding dimensions to different feature fields in a data-driven manner. AutoDim is a two-stage framework. The first stage aims to find the optimal embedding dimensions for each feature field, and the parameter retraining stage selects the embedding dimension and then retrains the parameters. During the first stage, a set of candidate embedding with different dimension is attempted. Then, in order to keep the output dimension unchanged, similar as auto-embedding and ESAPN, a transform layer is proposed to map the embedding into a same dimension. After that, we obtain the formal embedding for each value by computing the weighting sum of all their transform embeddings. Then, these formal embeddings are concatenated and fed into the MLP component. The architectural weights over the unified embedding are obtained upon the validation set, while the other model parameters are learned on the training data set. As for the dimension selection, to make the whole framework end-to-end differentiable, AutoDim search the dimension in a soft and continuous function via the Gumball softmax. During the parameter retraining stage, the optimal embedding with the largest weight is selected for each feature field, and then retrain the parameter to obtain the final model. In order to balance the search efficiency and performance, some work split the feature value into multi-groups based on the feature frequencies or the clustering, such as the NIPS and the DNIPS. At first, DNIPS use a feature broken stage to reduce the search space, and then group feature into multiple blocks, where the feature in a block share the same dimension. Then, DNIPS introduce a soft selection layer between the embedding layer and the feature interaction layer to identify the importance of each dimension in the feature embedding. To relax the search space to be continuous, during the search stage, a gradient-based bi-level optimization procedure is proposed. After the optimization, the non-informative embedding dimension will be proved with a predefined threshold. NIPS also claims that for some head features, they have more data and information. Therefore, using a large embedding is reasonable. Instead, for some tail features with less data, a small embedding size is enough. To further reduce the search space, NIPS divides the search space from both row-wise and column-wise perspective. NIPS decide single-site embedding search and multi-site embedding search and then use a RL-based solution to find the optimal embedding dimensions. Specifically, the original embedding matrix is split into multiple embedding blocks. Then a controller learns to sample embedding dimension. For the single-site embedding pattern, the controller sample one pair from the search space, while for the multi-site embedding pattern, the controller makes a sequence of choices. Finally, the selected embedding block will be concatenated to form the final embedding matrix. The controller is trained with the reward calculated from the main model over the validation dataset, which takes both the optimization objective and the training cost into consideration. The above-mentioned words are decided for the categorical features. Besides, Automl-based methods are also used for the numerical feature representation. A typical model is AutoDis, which is an automatic embedding learning framework for the numerical features. Existing representation approaches have some limitations. The first category uses the original or the transformation directly without learning embedding, resulting in the low capacity and the poor compatibility. The second one shares a single unified field embedding for all the numerical features in the same field, which is also low capacity. The most popular method is discretization, which transfers the numerical feature to the categorical feature by some predefined rules or models. However, this hard discretization mechanism is two-phase and may cause the SBD and DBS problem. AutoDis to overcome these limitations, AutoDis is proposed, which consists of three core modules: meta-embedding, automatic discretization, and the aggregation function. Specifically, AutoDis decides a set of meta-embeddings for each numerical field, which are shared among all the features. Then this meta-embedding can learn global knowledge from the perspective of each field. Then a differentiable automatic mechanism is leveraged to perform the soft discretization and then capture the correlation between each numerical feature and the meta-embeddings. Finally, an aggregation function is performed to learn the unique representations. Here is the comparison of the different methods. For the categorical feature embedding search, single embedding search method aims to search optimal embedding dimension for each feature value. Therefore, this method will face a huge search space. Another research routine is to group the feature value of a field based on some indicators such as the frequency, and then assign a row-wise group embedding dimension for all the values within the group. This method belongs to the group embedding search. As for the search strategy, includes gradient-based, reinforced learning-based, and regularization-based solution, where gradient-based is more popular. Then in this part, we will present some AutoML-based research for the interaction component in the deep recommender systems. Effectiveness modeling feature interaction is important for the recommender systems. Both low-order and high-order feature interaction play important roles to model the user preference. For example, the interaction behaviors between the app category and the time step is an important signal for the food delivery app. Besides, some high-order interaction, such as the three-order interaction among the app category, user, gender, and age, are very important for some video games. However, these interaction signals are hidden in the data and is difficult to identify. Therefore, the challenge of modeling feature interaction are threefold. Firstly, enumerating all the feature interaction needs large memory and computational cost. For some industry dataset with hundreds of feature fields, which has a lot of feature interactions. Besides, it is difficult to be extended into a high-order interaction and may contain many useless noisy interactions. Secondly, using human effort to identify the important feature interaction is time-consuming and requires high-level cost. Besides, this human picking method may miss some counterintuitive but very important interactions. Finally, the interaction function needs expert knowledge to decide, such as the inner product, outer product, and so on. Moreover, the interaction function are capstan for all the feature interactions, which is suboptimal for the recommender systems. Therefore, selecting important feature interaction with suitable interaction function is very important. Depending on the search space, the existing methods can be categorized into three groups: feature interaction search, interaction function search, and interaction block search. Feature interaction search aims to search the beneficial feature interactions. Based on this, interaction function search further search suitable interaction functions for different feature interaction pairs. The last one is the interaction block search, which takes the original feature as a whole and search the optimal network with predefined operations. The first one is the feature interaction search, which search the beneficial feature interactions and drop some noisy interaction signals. AutoFizz is the first work for the automatic feature interaction search. The major motivation is that not all the feature interactions are useful, and some noisy interaction signals need to be identified and filtered. AutoFizz is consists of two stages. The search stage is designed to detect useful feature interaction, while the retrain stage retrains the final model with the selected feature interaction from the former stage. During the first stage, AutoFizz enumerate all the feature interactions and introduce a set of gates to indicate the importance of each interactions. To make such process differentiable, AutoFizz relaxes the search space to be continuous by defining architecture parameters alpha. Since the feature interactions are jointly learned with the architecture parameters, the coupling of the scale will lead to the unstable estimation. To solve this problem, AutoFizz used the batch normalization to ease the scale issues. Besides, the GRDA optimizer is leveraged to obtain a stable and sparse architecture parameters. Therefore, in the retrain stage, some architecture parameters with small values will be abandoned, which means that cutting some unimportant feature interaction. Finally, the model will be retrained to fine-tune the model's parameters. However, the limitation of stage, each feature is possible to be selected into a feature set or each order. In the feature grouping stage, the selection of useful feature interaction at a given order is treated as a structural optimization problem. Specifically, architecture parameters are introduced to indicate whether the feature is selected into feature set at a given order. Then, to make the selection differentiable, AutoGroup relaxes the binary choice of a feature being selected by a feature set to a softmax over two possibilities. The search space is further relaxed into continuous, and the optimization is approximated by introducing the Gumbel-Somax trick. With the Gumbel-Somax, the process of grouping feature into different feature set is trainable via the back propagations. During the interaction stage, the representation of feature set is defined via the founder weighted sum with the learnable network weight W. Then, inspired by the FN, the p-order interaction is given below. By doing this, the time complexity of the high-order interaction can be reduced. In summary, AutoGroup used the Gumbel-Somax to group the features into high-order interaction and then present a high-order interaction calculation form. However, although AutoGroup solved the efficiency and accuracy dilemma through the feature grouping, it also ignores the order priority property. The order priority property means that the higher order feature interaction qualities can be relevant to that degenerated low order ones, which is a very important property for the high order interaction modeling. Therefore, FICE provides another solution. It regards the original feature as a feature graph and then model the high order feature interaction by the multi-layer convolution or the GNN so that the huge search space can be reduced. Besides, to keep the order priority property, FICE make the adjacency matrix of each layer depend on the previous layer. To be specific, FICE defines an adjacency tensor to indicate the feature interaction at each order. With an adjacency tensor, the dedicated graph convolutional operator produces the node representation layer by layer. For example, for the k order, the node representations can be aggregated by the k-1 order and the 0 order. Therefore, the node representation at the k layer corresponds to the generating k+1 order interactive features. From the perspective of feature graph, the task of generating interactive features can be further formulated as a bi-level optimization problem. To make the optimization more efficient, FICE use a sub-adjacency tensor for propagation at the k layer. When the calculation still depends on a binarized adjacency tensor. Finally, after the optimization, the beneficial feature interactions can be derived with the well-learned adjacency tensor layer by layer. Besides searching beneficial feature interactions, searching optimal interaction function for each feature interaction pairs contributes to better capturing the informative interaction signals. Calibrating filtering is a very important topic for the recommender systems, which use the inner product between the user and item embedding vectors for prediction. However, besides the inner product, there are many human-designed operations such as plus, minus, max, concat, autoproduct, and so on, which are also used in various recommender tasks. Is that an absolute best interaction functions? The answer is not for the research SIF. The optimal interaction function depends on the task and the dataset. SIF is designed for selecting different interaction functions across different datasets. It automatically derives a suitable interaction function for the CF task, which consists of micro search space referring to element-wise MLP and the macro search space, including several predefined operations. SIF first search for a nonlinear transform on each single element, and then combine this element-wise operation on the vector level with different operations. A bilevel gradient-based search algorithm is then leveraged to relax the choices among operations in a continuous space. Finally, a specific network can be developed for the different dataset. Auto feature extends the interaction function search to the multi-field high-order scenarios. The motivation for the auto feature is twofold. Not all the feature interaction between each pair of fields need to be modeled, and not all the useful feature interactions can be modeled by the same interaction functions. Therefore, auto feature utilize several micro networks with different architectures to model these feature interactions. The search process is achieved by an evolutionary algorithm with the naive-based tree. Firstly, auto feature chain a naive-based tree to classify different network architectures according to the prediction accuracy, where the tree tends to classify the most well-performed network into the leftmost leaf subspace, such that the next generation can be more efficient. Then sample leaf nodes from this subspace based on the Chinese restaurant process. The top two samples with the highest accuracy will be picked to perform a crossover and several mutations. Then the result architectures will be checked whether belongs to the desired space. The whole search procedure continues until the desired accuracy is achieved or the maximum number of steps is reached. Searching appropriate interaction function for different feature interaction may bring a huge search space and high overhead. Therefore, one straightforward idea is to take the original feature as a whole and search the optimal network with predefined operations, which belongs to the interaction block search. Auto CTR is one of the representative work for this kind, which decides a hierarchical search space by abstracting the low features and operations such as MLP, FN, and the dot product into the virtual blocks. Then these blocks are further connected as a graph. Both the block hyperparameter and the connection among blocks are to be searched. Similar as the auto feature, auto CTR utilizes a multi-objective evolutionary algorithm with the architecture level learning to rank guidance to search the optimal architectures. Firstly, several architectures are random sample and then evaluate. Then a multi-objective survival selection process is designed, and several metrics such as the model fitness, age, complexity are taken into consideration. Therefore, a few top performance architectures are selected as the population for the parent selection. After getting the population, the next step is the parent selection. The goal of parent selection is to select an architecture from the population for generating a good performance of strings. To balance the selection intensity and the diversity, Auto CTR designs a nonlinear ranking distribution and proposes a ranking-based parent selection process. Finally, a parent architecture will be sampled in this process. Then a mutation process is used to generate the neighbors. A learning to rank strategy is used to learn the relative ranking among architectures based on a pairwise ranking loss and the gradient boost tree learner. Finally, the best neighbor as the offspring will be added into the population. And this search procedure continues until the desired architecture is sampled or the maximum number of steps is reached. To further improve computational efficiency, AutoPI utilizes a gradient-based search strategy for exploration in a more efficient search space. AutoPI decides a hierarchical search space with block connecting to a graph, where the interaction cell formulates the high-order interactions, while the example cells formulate the example of the low-order and the high-order interactions. Then the gradient-based search strategy is adopted in the AutoPI for the efficiency. AutoPI first introduced the architecture parameter for continuous redirection on the search space. By doing this, the architecture can be optimized by the gradient-based methods. A bi-level algorithm is used to learn the architecture parameters and the weights of operations. The architecture parameters are optimized upon the validation set, while the model's parameters are learned on the training data sets. Here is the comparison of the different methods. In summary, depending on the search space, existing method for automatic feature interaction component can be categorized into three groups: feature interaction search, interaction function search, and the interaction block search. Feature interaction search aims to search the beneficial feature interaction. Based on this, interaction function search further search the suitable interaction function for the different feature interaction pairs. The last method is interaction block search, which takes the original feature as a whole and search the optimal networks with predefined operations. As for the search strategy, including the gradient-based methods and the evolutionary-based solutions, where gradient-based methods is still more important. The next part is comprehensive search and the system design. Yejing Wang will present this part. Thank you.
Okay, thanks, Mr. Burton. Let me share my screen. Can you see my slides now?
Yes.
Okay, this is Yejing Wang from City University of Hong Kong. Mr. Burton has introduced an automated machine learning methods searching for the optimal embedding components and the future interaction components. I will continue to introduce some latest works about comprehensive search and system design. Comprehensive search means the approach searches for several parts at the same time. For example, if a framework searches for both the embedding side and the interaction function, then it is a comprehensive search. And the system design search means an approach applied to achieve the optimal architecture beside the aforementioned components. For example, the loss function is also an important part for model performance. Approaches search for the optimal loss function could help us to design more effective deep recommender systems. This kind of works could be regarded as system design search. Here is a table including all papers in my talk. I will introduce 3 works for comprehensive search and 3 works for system design. More related papers could be found in our survey. I first introduce works for comprehensive search. The first work is AMEIR. Authors suggest that deep recommendation models could be divided into 3 parts: behavior modeling for sequential features, future interaction for non-sequential features, and the future interaction and the multi-layer perception for model inference. Plus, existing deep recommender systems are hard to suit all scenarios, and the search space of previous automated deep recommender systems are restricted. For these reasons, authors propose AMEIR, searching for these 3 parts to achieve an adaptive model. To be specific, they search for the sequential modeling architecture, future interaction candidates, and the multi-layer perception dimensions. Compared with the deep recommender structures we mentioned before, this work takes sequential features into account. In this paper, the whole search space correspondingly consists of 3 subspaces. The first is the subspace for behavior modeling. In this subspace, authors aim to search for L blocks. L is a predefined hyperparameter. The structure of a block is visualized in the right feed. There are 3 units in each block: normalization, layer operation, and the activation function. The computation of a specific block is listed under the feed. Predefined candidate sets of these units are also listed. For example, we could select a convolutional network or recurrent network as the layer operation. The second search subspace is interaction exploration. In fact, AMEIR fixes the interaction function as hardman product and only searches for future interaction candidates. For the third search space, this paper searches for the output dimension of each linear transformation and the following activation function. The output dimension should be smaller than the input dimension. The detailed constraint is formulated, and similar to subspace 1, the activation function is selected from another predefined candidate set. The overall strategy of AMEIR is one-shot random search. AMEIR searches for a host recommender system in 3 steps. The first step is search for behavior modeling blocks for sequential features. With only sequential features input, AMEIR evaluates the performance of such architecture with a predefined multi-layer perceptron. The second step is searching for future interaction. The strategy of this step is a combination of one-shot random search and a sequential model-based optimization. Specifically, future interaction set is progressively enlarged. Only selected features interaction from the previous order will be candidates for next order interaction. The evaluation is conducted with another predefined multi-layer perceptron. In the last step, AMEIR allocates a weight matrix with the maximum dimension for each layer and select a submatrix according to the search dimension. The second work I want to introduce is AIM. It is an extended work of AutoFIS. In AIM, authors search for 3 parts of deep recommender system: future interaction function, and the embedding dimension. AIM utilizes gates to control the model architecture. Whether a gate would open or close depends on the contribution of the corresponding architecture to the final performance. In other words, non-predictive future interaction, ineffective future interaction function, and the redundant embedding dimension would be dropped. The process of AIM is visualized on the right. It first searches for the future interaction and the corresponding interaction function, then searches for the optimal embedding site. The framework is optimized by gradient descent. The third work is AutoIAS. This framework searches for 5 components of deep recommender systems: embedding side, projection side, future interaction function, and the multi-layer perceptron structures. The projection side is a unified dimension for future interaction. AutoIAS generates the optimal architecture based on knowledge distillation together with reinforcement learning. To be specific, different from ordinary parameter sharing strategy, this framework regards the network with the most parameters as a teacher architecture, or generated networks as a student network. Then AutoIAS transfer knowledge from the teacher network to the generated architectures, achieving a similar target to the ordinary parameter sharing strategy. The architecture generating policy is trained by reinforcement learning. Next, I will introduce 3 works for system design. First, I want to share auto loss. Most existing deep recommender systems leverage a predefined and fixed loss function. It leads to a suboptimal recommendation quality and training efficiency. while some other works exhaustively search or manually set weights and fuse multiple loss functions by weighted sum. They are computational intensive and neglect various convergence behavior. This work aims to search for appropriate loss function according to the different convergence behavior. Here is the framework of auto loss. I first introduced the forward propagation process. It could be divided into 4 steps. First, the deep recommendation model makes the prediction. Then we calculate all candidate losses. Subsequently, according to the convergence behavior of data examples, the controller generates weights for each loss. And finally, we get the weighted sum of losses. Then we need to optimize the framework by backward propagation. There are 2 sets of parameters should be optimized, the controller parameters and the deep recommendation model parameters. Auto loss alternatively updates these parameters. To be specific, the deep recommendation model parameters are updated on training data and with the controller parameters fixed, while the controller parameters are updated on validation set with the deep recommendation model parameters fixed. This design helps to tackle the overfitting problem. Next, I want to share AutoGSR. It is a framework searching for the optimal graph neural network architectures to perform session-based recommendation. Session-based recommendation aims to predict the user preference based on several previous actions. Many works are proposed to convert the sessions to graph and apply graph neural networks for recommendation. Authors suggest that all information in a session graph could be divided into 3 types: long-range dependencies, local context information, and the semantic relation information. Plus, to handle this information, we could use these 5 kinds of session graph and the corresponding graph network architectures. However, existing methods only consider a single type of session graph. To utilize the advantages of all graph types and capture all information, authors apply automated machine learning. Specifically, the search space of AutoGSR is 2-level: session aggregation and layer aggregation. On session aggregation level, authors search for the optimal session graph for each layer. The candidates are aforementioned 5 kinds of graphs. On layer aggregation level, authors search for suitable operation to aggregate the information of each layer. The candidates are listed. It is optimized by continuous selection and gradient descent. The last work of my talk is AutoFT. AutoFT is designed for transfer learning recommender systems. Automated machine learning techniques are applied to decide whether some parts of a pre-trained model should be frozen in fine-tuning. It could help to tackle the overfitting problem. It searches for field-wise and layer-wise parameters. The field-wise parameters are the embedding metrics of each future field, while layer-wise parameters are parameters of deep and cross layers for future interaction and prediction. It is also optimized by continuous selection and gradient descent. Next, Dr. Xiangyu Zhao would conclude the tutorial and give some future directions. Thanks.
Okay, thank you, Yejing. Let me share the screen. Can you see my screen?
Yes.
Okay, thank you. Okay, so this is the last section. And in this section, we will first summarize the tutorial and then provide some potential feature directions. So from previous sections provided by my colleagues, We know that AutoML can improve the performance of deep recommender system in a data-driven manner. And the existing AutoML work mainly focuses on searching the optimal embedding dimensions for the better feature representations and design appropriate deep networks to capture the feature interactions. And also design the comprehensive system architecture to better improve the model performance. So by introducing AutoML into the deep recommender system, we can automatically design the different models according to various data. This can improve the prediction performance and the model generalization. Besides, it's also helpful to eliminate the negative influence from human bias and error. And it can also significantly reduce the artificial and the temporal cost. So for the embedding component, the embedding dimension search methods can be divided into two categories, the single embedding search and the group embedding search. The former single embedding search, they search for the optimal embedding dimension for each feature value. And the later group embedding search, they first group the feature values and then assign the same embedding dimension for all the feature values within the same group. So therefore, the search space of the group embedding search is less than the single embedding search. And besides, we found that the automatic embedding learning for the numerical features are very limited. And as for the search algorithm, gradient descent is more popular because it's fast speed. Okay, for the interaction component, the existing work can be grouped into three types. First, the feature interaction search aims to search beneficial feature interactions automatically. And based on this, the second type, interaction function search, they further search the suitable interaction functions for the different feature pairs. And therefore, these two types of methods have a very large search space with the number of feature fields. And the third method is the interaction block search, which takes the original features as a whole and group the representative operations in several blocks so as to reduce the search space. So the search strategy includes a gradient-based and evolution-based method, where the gradient-based is more popular. And finally, for the comprehensive search, researchers usually design algorithms to search for each part separately. And for the system design, we could apply AutoML to many aspects, from the loss function to session search and the transfer learning. And for these two kind of works, gradient method is still the most popular search algorithm. Okay, so although many efforts has been made to automate the design of deep recommender system, there are still many opportunities for the future directions. For the feature embeddings, it is potential to combine the automatic feature representation with the model compression and quantization. And besides, multimodal features are widely used in the recommender system, and we can also learn their representations by AutoML. For the feature interaction, most work focus on the global feature interaction search, but the personalized feature interaction search for different users remain unexplored due to the huge search space. And besides, we can introduce more complex interaction functions from CV and NLP to generate more diverse interactions. For the comprehensive search architecture, existing works usually search for several parts of the deep recommendation model. However, there are few works they rarely search for the multiple components simultaneously. Current work, they just search for each part separately and then combine them for final deep recommendation model. So this might result in the suboptimal recommendation performance. And then for the AutoML algorithm, existing works just directly transfer some algorithms widely used in CV and NLP to the deep recommendation models, which may be suboptimal. Thus, it's important to design more suitable search and evaluation methods for the recommendation scenario. Moreover, there are some other potential research directions. The first one is, according to different requests, we can adaptively search different submodels or sub-architectures, which is very beneficial for the industry. Besides, multitask learning that consider the different revenue target is one of the most important techniques in the industry recommendations. Thus, it's worthy of designing an automatic algorithms for the multitask recommendations. And at last, users' historical behaviors contains different dimensions of their interests. Therefore, we can automatically retrieve the beneficial historical behaviors to better model user preference. Okay, that's all for our tutorial. If you are interested in this topic, please refer to our survey for more details. Thanks for your listening. Any questions?